Rockets don't push against air. They don't have wings. And they certainly don't grab onto space. In fact, rockets work best in a vacuum where there's literally nothing to push against. So how does a machine weighing millions of pounds launch itself off Earth, accelerate to thousands of miles per hour, and escape gravity entirely? It seems to defy logic. Let's break it down simply first, then for real. The core idea of a rocket is surprisingly simple. It moves forward by throwing stuff backward really, really fast. That's it. Technically, this is a perfect demonstration of Newton's third law of motion. For every action, there is an equal and opposite reaction. When a rocket expels mass, in this case, superhot exhaust gases out its nozzle at incredible velocity, the rocket itself experiences an equal force pushing it in the opposite direction. We call that force thrust. Critically, the rocket doesn't need air or the ground to push against. The entire interaction happens between the rocket and its own exhaust gas. It's an internal system. This is the fundamental reason why rockets work so perfectly in the complete emptiness of space. So, how do we make that push, that thrust, as powerful as possible? Think about it this way: the faster and the heavier the stuff you throw backward, the more push you get forward. The technical formula is simple: thrust equals the mass flow rate multiplied by the exhaust velocity. This means you can increase your thrust in two ways: either expel more mass per second, just burn more fuel, or expel that mass at a higher velocity. Chemical rockets are designed to do both. They burn a fuel and an oxidizer to create extremely hot, high-pressure gas. The hotter the gas and the lighter its molecules are, the faster they can be shot out the back. This is precisely why hydrogen-oxygen engines are so efficient. Hydrogen is the lightest element in the universe, so its exhaust particles can achieve mind-boggling speeds. But wait, there's no air in space, so how does anything burn? A jet engine on an airplane sucks in air from the atmosphere to burn its fuel. Rockets can't do that. They have to be self-sufficient, like a deep-sea diver carrying their own oxygen tank. So, every rocket carries two things: a fuel, like liquid hydrogen, kerosene, or methane, and an oxidizer, which is usually pure liquid oxygen, often called LOX. These two propellants are stored in separate tanks at cryogenic temperatures and are then pumped into a combustion chamber. Inside, they mix and react violently, producing gas at temperatures exceeding 3,000 degrees Celsius, hotter than most volcanoes. The chamber has to withstand this insane pressure and heat. To stop the engine from melting itself, engineers use a clever trick called regenerative cooling. The freezing cold fuel is circulated through tiny channels in the engine walls before it even enters the chamber, absorbing the heat and keeping the metal intact. Now, all that hot, high-pressure gas needs to be turned into pure speed. This is where the nozzle comes in. It's the real magic maker of a rocket engine. A rocket nozzle isn't just a simple cone. It's a very specific shape called a converging-diverging, or de Laval nozzle. Here's what happens inside. The hot gas from the combustion chamber enters the narrowest part, called the throat. As it gets squeezed, it accelerates, reaching the speed of sound, or Mach 1, right at the throat. Then, as it enters the wide, bell-shaped part, it expands supersonically. This rapid expansion is what converts all that chaotic thermal energy, the heat, into directed kinetic energy, or motion. It massively increases the exhaust velocity. You might notice that engines designed for space have huge, wide nozzles. That's because, in a vacuum, the gas can expand more freely, making the engine more efficient. Near the ground, the nozzle has to be smaller to work against atmospheric pressure. Okay, so we have thrust. But rockets don't just go straight up forever. That would be a huge waste of energy. To get into orbit, you don't need altitude as much as you need speed, sideways speed. To stay in low Earth orbit, an object needs to be traveling at about 7.8 kilometers per second horizontally. So, a rocket launches vertically at first, just to punch through the thickest part of the atmosphere. But very quickly, it begins to perform what's called a gravity turn. It gradually pitches over, tilting its trajectory to start building that crucial horizontal velocity. Every second a rocket spends just fighting gravity is a second it's wasting fuel. Orbit is not about being high up. It's about going so fast sideways that as you fall back toward Earth, you constantly miss it. This brings us to one of the most brutal realities of spaceflight, captured by the Tsiolkovsky rocket equation. The simple version is this: as a rocket burns fuel, it gets lighter. As it gets lighter, the same amount of thrust makes it accelerate faster. The equation itself is a bit more complex, but its implications are staggering. It shows that most of a rocket's initial mass, often over 90%, is just fuel. It also shows that even small improvements in exhaust velocity make a huge difference. But most importantly, it reveals that adding just a little bit of extra payload like a satellite requires an exponentially larger amount of fuel. This crushing math is the main reason rockets are built in stages. Think about it, once you've used up the fuel in a tank, that tank is just dead weight. Carrying it is incredibly inefficient. Staging is the solution. By building the rocket in sections or stages, you can just drop the empty parts mid-flight. The first stage fires, gets the rocket to a certain altitude and speed, and then separates, falling away. The second stage, now much lighter, ignites its own engine and continues the journey. This allows the rocket to achieve a much higher final velocity than a single-stage rocket ever could. Modern reusable rockets, like SpaceX's Falcon 9, take this a step further. They don't just drop their stages. They land them, allowing for reuse, which dramatically cuts the cost of getting to space. Finally, none of this works without an incredibly sophisticated brain. How does a rocket steer? It doesn't have a rudder. It steers by tilting the direction of its exhaust. Most modern rocket engines are on gimbals, which means they can pivot a few degrees in any direction. By tilting the engine, the rocket can precisely control its orientation and trajectory. In the vacuum of space, it also uses tiny reaction control thrusters, little jets that puff out gas to make fine adjustments. All of this is managed by an onboard flight computer, which uses an inertial navigation system packed with gyroscopes and accelerometers to know exactly where it is, how fast it's going, and which way it's pointing. The control has to be perfect. A tiny error of just 1 degree in its flight path could cause it to miss its target orbit by hundreds of kilometers. So, to wrap it all up, rockets work by throwing mass backward at extreme speeds, a perfect application of Newton's third law. They convert the chemical energy in their fuel into pure momentum. They do this by carrying their own oxygen, surviving self-generated infernos, and using masterfully designed nozzles to turn heat into velocity. They manage their mass ruthlessly by shedding dead weight, and they navigate with pinpoint precision. They don't push on air. They don't cheat physics. They obey it with brutal efficiency. And that is why, even after all these years, space is still hard. Thanks for watching. If you found this fascinating, hit that subscribe button for more deep dives.